On behalf of the University of Hyderabad and the School of Physics, I welcome Professor Jayanta Bhattacharjee for this second lecture, distinguished lecture of our school. And I request Professor Bhattacharjee to come to the stage, to the dais, and Professor Arun Agarwal, our Pro VC, to come to the dais, and Professor Ashok Chatterjee, our senior most professor in condensed matter physics, to come to the dais. I'm very happy to welcome all of you to this lecture, and I hope that you will learn a lot from it, and I hope that you will enjoy it. Now I would ask, I won't go into details of the School of Physics because everybody knows in this audience, I think everybody knows about the School of Physics. So without further ado, I would request Professor Chatterjee to introduce the speaker.
Pro Vice Chancellor, Sir, Dean, School of Physics, Professor Jayanta Kumar Bhattacharjee, colleagues, students, and friends. It's a great pleasure for me to introduce today's distinguished speaker, Professor Jayanta Kumar Bhattacharjee, who of course does not need any introduction at all. He's a very well-known physicist in this country, but still I'd like to say a few words about him for the benefit of our younger colleagues here, and the students who are in the audience. If I'm asked to introduce Professor Bhattacharjee in one sentence, then I would say he is one of the finest theoretical physicists of this country at the moment, and is also an outstanding teacher. Professor Bhattacharjee did his master's from University of Calcutta in 1975. Then he went to US and joined the University of Maryland and did his Ph.D. with Professor Richard Ferrell in 1979. Then he went to University of California for his postdoc, spent about 2 years there, and then came back to Maryland again and spent another 2 years. After that, he moved to Germany for his next postdoc, and he returned to India in 1982 to join the Department of Physics, IIT-Kanpur, as a faculty member, where he eventually became a full professor. After serving IIT-Kanpur for about 13 years, he came back to Calcutta in 1995 to join IACS, which is Indian Association for the Cultivation of Science, as an Mahendralal Sarkar professor, which is a very, very prestigious position. After serving IACS for about 12 years, he joined SN Bose National Centre, Kolkata, in 2008 as a distinguished professor, and in 2012 he moved to HRI-Allahabad as a director and superannuated from there in 2017. And last year he joined the Department of Theoretical Physics, IACS, as a Distinguished Emeritus Fellow. Professor Bhattacharjee shot into fame very early in his career for refining the dynamic scaling theory for the critical phenomena around the lambda point of liquid helium-4. In fact, his work was cited by Kenneth Wilson in his Nobel lecture. He is also very well known for his fundamental contributions to the finite size renormalization group, critical ultrasonics, hydraulic jumps, critical viscosity, pattern formation, rotating turbulent fluids, and non-equilibrium statistical mechanics, to name a few. For his outstanding contributions to physics, he has been elected as a Fellow of Indian Academy of Sciences and also a Fellow of National Academy of Sciences. Professor Jayanta Bhattacharjee has authored or co-authored about 5 books which are very, very popular, and he has published more than 250 scientific papers in international journals of repute, which include 14 PRLs. He has supervised 24 Ph.D. students in different areas of physics. One unique quality about him is that he encourages even undergraduate students to pursue fundamental research. In fact, many undergraduate students and master's students have returned research papers with him. Professor Bhattacharya is a great inspiration for the entire scientific community in the country, and we are extremely happy and fortunate to have him here to deliver a distinguished lecture on pattern formation. Thank you.
So I request Professor Agarwal to chair the lecture, and I request Professor Bhattacharjee to please give his lecture.
Right. So, after Ashok's introduction, it's actually difficult to do justice to it, to what he said, but we'll see. But before I start out, I would like to express my sincere thanks to the university as a whole for inviting me. The university for inviting me for this lecture. I'm grateful to the Vice Chancellor, to the Dean Vindhwamba, to Shaul Viswas, who was the engineer of this, I guess, and all of the other faculty members of the physics department, and for making this visit possible. So, with that, I would like to get started. The point that I want to make is very simple. It is about the various kinds of temporal and spatial patterns that we see around us. Pattern, as the word suggests, is something which is a question of recognizing you see a pattern or understand a pattern if you can recognize one, and recognition means that you see one piece and you see another piece and you require that this is the same as that. So in that sense, pattern has a repetitive property. So it repeats itself after a period, if it's a pattern in time, after a certain length, if it is a pattern in space. So periodicity is the simplest criterion for recognizing a pattern. I will, for this lecture, restrict myself entirely to the simplest possible situation of recognizing a periodicity, but that is not to say that things which are not periodic do not have a pattern. As I think it was Weil who once remarked that the absence of symmetry is never an indication of asymmetry, it only indicates a deeper symmetry. So same with pattern, the absence of the period, a periodic repeat is not the absence of pattern, it just says something more complicated is going on. It is possibly a quasi-periodic that is characterized by two irrational frequencies, as in the Parthenon in Greece. Many of these Vedic tablets that are described in terms of the irrational numbers, and then more complicated things of the similar nature, but those we'll leave behind today and only focus on the simple period, and the issue is what determines the period. And the answer is that the period is always determined by two conflicting issues. So there has to be two conflicting physical effects which would have to come to a compromise to set up the length or the time which characterizes the pattern. So that is the answer that one needs to remember. If you forget everything else about the talk, the one thing to remember is that if you ever see a repeating pattern and it repeats after certain number of days or seconds or what have you, or after a few inches or meters or whatnot, you always, why did it get formed? And to answer that, it always pays to look at the physical effects, particularly competing effects. Why would there not be any scale to begin with? And then what is it that tries to cause a scale, and the compromise would give you the actual scale. So that is what we are going to discuss. And the first one is, we'll talk about length scales mostly, because patterns are nice to look at if it is in space. But it is the easiest to start with a temporal pattern, which you are all familiar with, that for example, that seasons repeat after a year. The kind of weather that we have over here today, cloudy with rain, a possibility, would be repeated a year later. And it is determined by the position of the earth vis-a-vis the sun, and the position repeats after 365 days. Question is, what settled the 365? What were the two opposing causes which led to this settling for 365 days? The cause, to understand that, you go back to the formation of the large masses splintering off, giving rise to planets and stars. And you have these things at formation buzzing off at enormous speeds. And so you can imagine the earth broken off from something or other, traveling along some particular direction, whatever the initial velocity was at its time of birth. And so it would have continued, because that's what Newton's law says it should. No forces, no change in direction of motion or in speed of motion. So on it would go, wherever, to the end of a possible scale of the universe. But somewhere along the line, it encounters this star called the Sun, which has a strong gravitational pull, and it tries to pull the Earth towards itself. So there is the initial velocity, which is quote unquote God-given, and along that merry path, it would have, in a path of initial condition, the Earth would have continued. But comes this different, the conflicting presence or action of the Sun, which says, I would rather make it fall towards me. The compromise is, but it's trying to move off in this direction. So trying to make it fall towards me means that it has to turn a bit. Now turning a bit, it would again try to go off in the direction in which it was, and the Sun wants, and so it turns a little more and a little more. And the eventual settlement is for an orbit which is able to go round the Sun, and that particular orbit where the Sun's pull balances the tendency of the Earth to fly away with velocity v is exactly the orbit that we have today, the orbit whose period around the Sun is 365 days. So that is the temporal pattern that one has to keep in mind, that a very standard situation the Earth going round the Sun is a temporal pattern and had to be formed as a conflict between inertia and the gravitational attraction of the Sun. So that's that. As this transparency says, we'll concentrate on one length scale situations, that is the spatial pattern that we'll be talking of, and the scale will emerge as a result of a tussle between two competing effects. So without the pattern, there is always going to be an uniform state. The uniform state for the Earth would have been just to go away with uniform velocity, and that's it. And so there is going to be a uniform steady state, which nature could have preferred. So it can't. The preference is lost because there comes a competition, and out of the competition grows the pattern. So we'll be to understand patterns, we would need some everyday physical forces and so on and so forth. So that's what I want to catch up with you in 5 or 10 minutes. What are these are no longer parts of curriculum in basic training very often. So it's good to refresh oneself about this. First is surface tension. Surface tension is this effect that if I break a clinical thermometer, well, at least some of you might have seen a clinical thermometer. That's also not something which is particularly used these days. But if you have seen one and ever broken one, you will find that clinical thermometer contains mercury. The mercury spills out and falls into little small globules on the table or on the floor or where have you. So these small globules, if you drop water on this table over here, it will not form a globule. It will sort of flatten out. The mercury, however, forms a globule. Why is that? That's the property of surface tension. Surface tension says it's a force which says that the surface area, which tries to minimize the surface area. It's a surface effect, that it's the molecules at the surface which are asymmetric in that they are attracted by the molecules inside and don't have any effect from the molecules outside, because outside is air or much rarer material. In that case, the surface, which the molecules on the surface feel inward force and would try to sort of make the surface the minimum possible, and it is this force of surface tension which sort of tries to pull the surface inwards was going to be a big player in some of the things we want to talk about. So if there was no, and why did this water not be spherical? Because there is, the mercury is very heavy, so but its surface tension is huge. The huge surface tension allows its the gravitational effect to be minimum, and it sort of is a sphere. The water, on the other hand, has a much lower surface tension, so the gravity pull is as important as so it's not that it is sort of spread out all over, but it is a kind of a flattened out drop. The water then would become, so it's gravity versus surface tension then, the water drop then would become, if there is no gravity, it would be completely spherical. And that's what happens if you watch a falling dewdrop. A dewdrop, when it detaches itself from a leaf, when it on the point, same is true for a teardrop. when it detaches itself from the leaf, it's in the shape of a pear. It's sort of like this over here, and then as it falls in free fall, the gravity is gone and it just becomes a perfect sphere. So falling free fall under gravity, which eliminates gravity, makes the liquid a perfect sphere. So that's the first force that one talks about. That's the surface tension. This figure tells you what I told you verbally, that this, I want to go, yeah. So this is where we are. I mean, there is a net force downwards over here, but over here there is no net force at all. That's the surface molecules have it, and that's what makes a needle float on the surface of a liquid. And that's what we talked about. Once again, the needle and so on. And here is zero gravity situation, free fall. Somebody switched off the machine of the rocket in Tintin's comic, and here is the Captain Haddock's whiskey coming out in a perfect sphere. All right, so that's surface tension. The next is heat conduction. So if you, conductivity, that's how heat gets transferred from one end. If I heat this end over here, if this is a block, heat this end over here, heat will so the point is that it's a question of different materials have a different kind of thermal conductivity. If I took some water and heated it, I would still be able to touch the top surface for a while until it becomes really hot. If it is a metal like iron and I heat it from below, it would be almost immediately impossible to touch the top. So the thermal conductivity sends heat from the bottom where it's being heated to the top where it's not being heated, and different materials have different thermal conductivities. The metals do it very well. There is a question of diffusion, which is a question of having a large concentration somewhere, and so you have a large amount of salt, let's say, put some large amount of salt in a heap in water, and slowly the salt is going to move out and fill up the entire, spread out uniformly over the liquid. The process by which it does it is diffusion. The solute moves from regions of high concentration to regions of low concentration. So that's the picture. And the last one that I want to talk about is viscosity. That is the resistance to flow, resistance to movement inside a fluid. So if any object tries to move through a fluid, there is the fluid viscosity which would try to oppose its motion. So viscosity, thermal conductivity, diffusivity, surface tension, 4 properties of matter which have a large role to play in the patterns that we see. So that's, but now comes here this picture, Asian Paints ads from a few years ago, where it's this kid over here has just dabbled some paint on a wall, and the paint comes down, which is expected, that it's a heavier liquid, and it comes down displacing the air underneath it, but it is what is unexpected is that it comes with this characteristic sort of pattern which is characterized by a length which is the length from one minimum to the next minimum. So one minimum to the next minimum, more or less the same. it's not exactly the same in this picture over here, because there is the wall behind which has its effects and so on and so forth. But it is a question of this interface becoming wavy. The air and paint interface, the kid, when he, what he did was swept his brush across and there was a band, and the band is not the thing which would survive. The band has developed a pattern in over here. And the question is, what are the competing forces? What went on over here? So you would expect the thing, you expect the air below and the paint on top, that to be just separated and have a boundary. Well, this paint is heavier, so it has to come down. All right, you say that it comes down, and therefore it will just sort of push the air down. Pushing a liquid, a fluid, gas or air, is not so easy. Everything is more or less incompressible. Pushing somewhere would mean that it's incompressible. So if air is pushed down here, it would push back over here. So there is going to be a certain wavy, there is the possibility of a wave being formed. It is two incompressible fluids in contact. One tries to push down. If it succeeds over here, there will have to be a little pushback at southern adjoining. But what is the characteristic length scale? How do I calculate it? There is gravity pushing down. So gravity pushing down, because if the heavier fluid descends, there would be when that is what gravity would like to do. Heavy things come down, the potential energy decreases. So gravity bringing the heavier fluid down would decrease the potential energy of the surface. But now you are creating a surface, flat surface has the minimum area. But in trying to bring the heavy thing down, you can't bring it down without forming these ripples, because the fluid, both fluids are incompressible. And so you have formed these ripples. As soon as you have formed ripples, the rippled surface is bigger than the flat surface. So that costs energy, because the surface tension doesn't like it. So surface tension into extra surface area produced, that's the energy. And if you have the thing has dipped down by a certain amount, so that determines the how much energy has been released by gravity. Now, how much energy released by gravity, that can be calculated, and then comes the question of how much surface area can be produced. Now, you see, the point is that if it is an extremely wavy surface, then it would be more surface energy which would be required. If it is a very slowly undulating surface, then the difference from a flat surface is very small, and there would be very little surface energy required. So there has to be how much surface energy is going to be determined by the amount of gravitational energy that you have managed for the system by coming down a little bit. So that's a fixed amount of energy, and the wavelength would have to adjust itself to get the two energies to be equal. That's the wavelength that is characteristic over here. The characteristic wavelength that you see is got by a compromise between the gravitational effect, which says come down, and form a wave, but surface tension says no wave, I don't like the extra energy. So it's a compromise between these two effects over here. That's the calculation. At the end of the day, the wavelength of is the inverse of this. This is the wave number. The wavelength where the two energies match is the surface tension divided by the energy difference times gravity. So that's where that's the typical wavelength. How much does it work out to be? If I take, if it were water, then this would work out to be somewhere near a few millimeters, close to a so all right. So it's a few millimeters if it were water, which now done with paints, the surface tension is much larger, so you get a somewhat bigger wavelength. But now what's the effect? I mean, what example can I give with water or equivalent liquid like alcohol, which you do come across very often? That is, if I take this bottle over here, unscrew it, and turn it over, the water will just gush out. This length over here, the diameter is certainly of the order of a couple of almost an inch, a couple of centimeters. The characteristic wavelength is a few millimeters, which is much smaller. So there would be this wave formed, and out would come the water. Suppose it's one of these small homeopathic things. You turn it over, and then it does not come out, because you see that opening in that homeopathic bottle is smaller than the wavelength that would need to be formed in order for this pattern to get set. So therefore, most often of these bottles, you have to give it a little shake, that extra energy to get the medicine out. So that's the surface tension and at work against gravity, setting up patterns. This is the same thing which you saw with Asian paints done in a numerical experiment in the lab. Here is a lighter fluid, here is a denser fluid, and you see this neat pattern formed over here. As the fluid progresses, some other forces take over. Anyway, much said about that. Here's the next pattern that I want to talk about. Something which you have seen, and whether you want to see it or not, if you are in the open air, if it is hot and it's a dusty road and a hot day, and it suddenly showers a bit, and then the shower stops, out comes the sun and the water evaporates, you'll find that the dust has formed a pattern which looks more or less like a hexagon, something like what you see over here on the pavement. The same thing happens if you don't, on your windshield of the car, if you don't clean it, and there is a shower and the water dries off, there is the dust pattern on your windshield settles in that manner. You see it in the kitchen. If you take spices and water and boil it and let the water evaporate, you'll find that the spices don't form a hump or not even uniformly distributed. They form a almost hexagonal pattern on the surface of the pan. If you haven't done it, you can do it, go home and do it, and you will see that the spices are left behind and along some kind of a pattern. So what kind of a pattern is this, and what is behind it? This is a more, you see the hexagons. This is the the kitchen experiment done in a lab with explicit deformation put in at this point over here. It's a uniform slab at all places, except at this point over here, where the experimentalist put in purposely a little deformation. And you see these nice hexagons, more or less nice, formed all over here where the surface is flat. And you see the deformation over here. It's the hexagons get deformed because of the underlying non-flatness of it. And so that's a nice picture. And now comes the question of what is what. So what formed this? The process is a process called convection. What is a convection? Well, who are the competing things? I have this question of heating this fluid from below. If I heat the fluid from below, the heat will conduct the fluid and the top surface will start becoming hot. But that's not, if I increase the heat slowly, there will come a point, initially the fluid does not move. But then comes a point when this fluid, this heated fluid, starts moving. That heated fluid initially will not move, because if it tried to move, viscosity would be a problem. So viscosity would try to, why does it move at all? What is the upward force? It's a force of buoyancy. It's hotter over here, it's colder over here, so it is the force of buoyancy, lighter liquid here, heavier liquid over here, so the lighter liquid would like to move up because of buoyancy. So buoyancy is the driver. So driver would mean that, but there is a resistor. Who is the resistor? Viscosity resists and thermal conductivity resists. Thermal conductivity would say, look, it won't be possible to make this hot fluid from below rise, because as it goes, the hot fluid will have its heat conducted away, so it will no longer be hotter than its surroundings and it will drop back. So thermal conductivity opposes this motion of the upward motion of the liquid. Viscosity opposes it. The buoyancy says it must happen. The compromise is that the motion is in the form of a cell. So you go up and you come down, so that when these things sort of form a compromise, the gravity and the conductivity and viscosity, their compromise is to have a cellular pattern with a characteristic length scale. So this cellular pattern with a characteristic length scale is what you, so this essentially tells you the point that I made, that there is this question of viscosity opposing this, and there is the question of heat diffusion, which also enters the game. And so you see this pattern, this cellular pattern, coming out of a competition between gravity and viscosity and this, and the result is, so you see the result on, that's a kitchen or street-based result, which you see reflected in some cloud formations, not all, but for example, this morning the cloud over here had some, that whenever you see a cloud formation which looks like this, there is a certain name which I can't remember, but this is the picture, and when you have a picture like this is a cloud which is formed on the basis of convection. Whatever is going on this hot street with a shower or in the kitchen in a pan is what is going on in the clouds over here. We can shift to a very different thing, a pattern which you see in the giraffe, the cheetah, and the zebra, here, and very butterflies and so on and so forth. So there is a distinct pattern on this over. Now, how do I get about it? The issue is here the game changes a little bit. In all the examples that I gave you before, I could actually write down Newton's law. In every situation, there would be Newton's law to guide me. I write down Newton's law, look for the maths which goes with the words that I described, and the answer would give me the pattern. Now I have a situation where Newton's law is no longer valid. I have two pigments. If it's the zebra skin, I have two pigments, white and black. They would be, under normal circumstances, you take and mix some white and black, stir them up, and they would just sort of diffuse into a grayish background. But something happened which made the white and the black stand apart. And what happened is then you have to imagine. You have to write down for yourself the dynamics for the white and black pigment. What could have happened, what might have been the interaction between, what could have been the characteristics of this white and black, which would give you the pattern. The person who did this for the first time was Alan Turing. That's why all such patterns are known as Turing patterns. And Turing, known for code breaking, the architect of Britain's victory, aerial victory in the Second World War, and the computer wizard, is also the man behind the patterns over here. So what is the Turing pattern? Turing pattern says that you take this two diffuse, the black paint and the white paint, the two, so they diffuse. One of them, all species, all chemicals diffuse. So you have this black and white chemical, and one diffuses. Turing assumed that one diffuses more strongly, much more strongly than the other. There is one which is sort of autocatalytic. One of them is that is, it can sort of generate itself. But it also produces the other. Let's say the white is the activator. It can generate itself, but it also produces inhibitor, which is the black. So the inhibitor is the activator is an inhibitor which prevents the formation of the black. And this inhibitor diffuser, the difference in diffusion coefficient, the inhibitor diffuses, that is the one which diffuses much faster. So just imagine that what can happen is that I have this uniform gray. Let's say I have a little change at some point, little apart becoming a little more white and another adjoining part becoming a little more black. The white can produce itself, but it also produces a little more black, and the black can diffuse fast. So the black diffuses out and gets to the other side of the white, and so the white gets enflanked by two blacks, and that's what triggers the pattern. So white, once you have once instability is once a fluctuation takes place, fluctuations happen through various kinds of processes, whether it is temperature or something else or anything. There are, spontaneous fluctuations do happen in nature, and this spontaneous fluctuation giving rise to a little bit of discrepancy is now fueled, which says that becomes an instability, and you have, instead of a gray background, a black, white situation, provided the black and white paints have this property which Turing gave them. So this is where there is an attitude shift. Previously, Newton's law told you what to do. In this kind of problems, you see the pattern and you have to guess what kind of dynamics would lead to the pattern. So that's but it's a pattern, all right, and it has to be the primary difference between the black and the white is this: one is a activator, the other is an inhibitor. So there is this conflict. The conflict between the black and white results in a separation of black and white, a pattern which says, all right, this separation keeps us at peace. So it's a compromise once again. Here is the galaxy. You have this galaxy formation, one huge mass and then matter, gaseous matter breaks up into galaxies. what's the typical length scale? And then again, what is, you look for what kind of effects could have given rise to a length scale. So there is gravitational attraction, which would say if I have a mass of gas, I'd like to bring them together and form a clump. So gravity would like to pull them together. But if you try to bring them together, decrease the volume, the pressure PV equal to nRT. The pressure just increases, and pressure says we like to keep them apart. So there is the pressure which comes from this random motion of the molecules constituting the gas, and gravity which causes the gas. That sets up a compromise and leads to the typical size. That was the first estimate of a galaxy size called the Jeans length. So that's the galaxy, and the Jeans length is again a compromise between two opposing. And last of my examples is once again something that you see every day. Here it is, and again, if you have not, you can go and see for yourself. It's a kitchen sink. The water flowing from this tap over here hits the base of the sink and flows out and jumps at a certain radius. Here is the jump over here. You will notice that the flow is pretty uniform, laminar as the technical word is, from here to the to this radius, and beyond it the surface looks pretty rugged, pretty choppy, and so the flow is laminar over here, very likely turbulent over here, and there is it's a circle on which this transition took place, and this phenomenon is called a hydraulic jump. In this case, a circular hydraulic jump. You see it in different forms. At the base of a dam, you can't see the jump over here because of the the vapor the mist that is formed by the. But you can see it in a lab situation over here. That's controlled water flowing down fast from on that side, and then a jump at this point over here as it slows down. And here it is in a river when there is this what do you call this? Some particular tides, which tidal bores, which come in, and you see the same kind of phenomenon over here. So in the same, all of the same kind. What is the competition? What determines the radius of this jump? So what determines this radius of this jump is something quite funny. The water, there is obviously this question of water flowing out. So water flows out, hits the base over here and then flows out radially. As it flows out, it has to slow down. So, all right, it slows down roughly as 1 over the radius. Now, what are the waves in the water? So, the waves in the water, the most popular wave in the water is a ripple. So, ripple which is driven by wind and water. So, any amount of wind or surface fluctuation of any kind generates ripples in. So, ripples are the natural waves in this layer of water. And ripples could be flowing in or flowing out. So, there would be, the ripples could be either traveling inwards, or there could be ripples traveling outwards. If the speed of the water is very high, there will be no incoming ripples. The incoming ripples will be driven out by the water. So what you see over here is a competition between the ripple effect, the ripple speed, and the speed of the water. It is at this boundary over here that the two speeds have become equal. If you look at this region of the water of your sink, there would only be outgoing ripples. Over here, there will be both outgoing and incoming ripples. This only outgoing ripples over here, which gives it this rather laminar appearance, the choppy appearance over here coming from the both. But here is a perfect boundary, a boundary where the one of the incoming and outgoing waves is blocked. And that should ring a bell. So you look at where does one see blocking. A blocking is reminiscent of black hole, where you have light can't come out, it can only go in. So one-way traffic. The canonical example of a one-way traffic is a black hole, and you have where there is light going in only, and that's there. Outside there is only the incoming, and inside there can be both ways traffic. So now the question is, all right, is this a black hole analog? There is a technicality over here. This would really be, I mean, you have a blocked situation over here. Rather, the black hole would have no blocking over here. It's a blocked situation over here. So it is the other way around. It is more like a white hole. So if you want to be precise about it, the analog is a white hole. So this is an example of boundary, and here is the lovely experiment performed in 2012, which tells you that this is a boundary, that this is where the two velocities match by generating a ripple through this pipe over here, and you see the ripples propagating in the Cherenkov cone. So the Cherenkov cone is in materials when the electrons move faster than the speed of light and emit radiation. So that's the Cherenkov radiation, which is limited to a cone, and you see this is this situation over here. It is the velocity, the fluid flowing faster than the wave velocity, just as the electrons moving faster than the wave velocity in the medium, which gives rise to the Cherenkov. Here is the Cherenkov analogy. There is, and as you bring it in over here, you are going to see the thing close. This will become, as the ripple is formed over here and here and here, you see this closing of the. So that was a beautiful demonstration of what was going on. And so what we, I'm about to end, what we said was all right. I mean, if these are two white holes, maybe one can see the effect of collisions of such objects by having a sink with two taps. So this is courtesy Kharagpur IIT Mechanical Engineering team who set this up, and two jets coming out of two faucets over here, and you see when they are far apart, two individual hydraulic jumps, a little deformed over here, more circular here than over here. The previous bigger separation would have shown. So now they are bringing it closer together. So here you see where they are closer, now closer still. So it is, I mean, it's now a traffic. The boundary is where you can't go in or you can't go out. So you are going to form a wall. If it is really no go in and no go out, and this is material that I'm talking about, they have to go somewhere. So they have to go up and they have to form a wall. So wall formation is what one is looking at. And here you see at the interface a wall getting formed. And here is as beautiful a wall when they are close together. Here is as beautiful a wall of water as you can see. And then they get a little more ambitious and make the wall, make these two come even closer together. And then real gravity brings the wall down, and that collapse is a collapse of the whole setup. And that is time for me to stop. So thank you very much.
So we have time for a few questions from the audience.
Is there two such tabs? If I have little more, let's say circularly placed tabs.
Yeah.
Can I have some kind of cylinder?
Oh yeah, I mean an arrangement of tabs. Yes, you can play around with the pattern. But all right. It's difficult to convince people to do a little any more than they did do a couple of tabs to see whether patterns get formed in a and they do. For this one. Oh, all these are essentially low Reynolds number phenomena. So they are almost all of these that I have talked about are low Reynolds number flow. So characteristic velocity, characteristic length scale are divided by the kinematic viscosity is not very big. Not very big means roughly 10 to the power 2 or 10 to the power 3, but not certainly something like 10 to the power 5 or 6. Yeah. And the same for the convection business. It is Rayleigh number, which is the ratio of the buoyancy force to the is of the order of 10 to the power 3, and again not of the order of 10 to the power 6.
So the characteristic parameter is the
Reynolds number is a character. When it is a flow, let's say of this kind, when it is a flow of the convective variety, it is the Rayleigh number, which is essentially the Reynolds number for that kind of problem. So it is, I mean, yes.
I just regarding the pattern formation in the zebra and tiger, whatever you show, this is that memorized, right? It is not just two pigments through this computation of force reach to a phenomenon, but that is memorized and it is an evaluation which has taken place. So every zebra will have same pattern. So how does one can memorize these effects if it is purely two competing forces?
All right. It's all right. That's which would be very. What you are asking is that that is the skin pattern. Certainly, I mean, once there is particular. All right. If a particular zebra has a striped, if all zebras have striped skin, and it has to be built into the brain framework, then that would automatically transfer. Yeah, sure. I mean, that is certainly there. So there is the question of the pattern that you see over there is to a large extent inherited. But what is the trait that is being inherited? The trait that is being inherited is presumably the existence of these different diffusivity components. That unless the pattern could not have emerged, I mean, or if you go back to, I mean, wherever the zebra evolution started, the point is that there would have to be a question of the physical effect that would have to form the stripe is a question of having these two kinds of species sort of existing in the system, and that probably is just transmitted from, it is very unlikely that what your question really is, that if I have a zebra, the next generation of zebra would not turn out to be a cheetah, would not have a different stripe. So this at some point, this certainly gets etched into the memory in some way. So yeah, that certainly has. Yeah.
But in the case of radiation pins, don't you think viscosity also play a role?
In which one? In the radiation pins? Oh yes, sure. The initial, it is only the initial instability, the formation of the interface and the wave, which has a question of surface tension alone. Particularly in the case of the paints, because there is the wall sitting behind, viscosity has a much bigger role. But if this were a pattern formed in a situation which is more controlled, that is a bulk liquid sitting on a bulk liquid, then the role of viscosity would be minimized, and you would see. That's precisely why, this is not so. Yeah, that's precisely why, this has, pretty, non-uniformity over here, viscosity over here, not allowing this to move, this moves down much further, and so on. So the role of the wall is very prominent over here. When it is a more engineered situation, as in the lab, where the viscosity was there, but it was sort of controlled, it only shows up in the later fingerings, but the initial step is without viscosity.
Are you saying that sound cannot propagate from one region to another?
No, sound is not the player. It is the ripple. Only the ripple which cannot propagate. Sound is, with sound there is a different, there is, in the B.Sc, in the superfluids, the sound plays a role. That's where the sound speed becomes the wave speed. Yeah, but not in this case. It's the ripple.
So this SN belt actually is a discoelastic.
Which one?
SN belt.
Yeah.
So the structural resistance times are actually much bigger than water. So therefore, the patterns are also partly governed by the elastic properties of the.
Yeah, sure. As I said, the substrate, the paint has viscosity, but the effect that I'm talking about is only the initial effect, where a flat interface becomes a deformed interface, and that is a pure surface tension effect in the beginning. So as soon as it starts moving, viscosity takes over. In the paints, the viscosity is far more pronounced than in, let's say, bulk air and bulk water.
Yeah. There are this quantum Hall effect, which is also incompressible fluid.
Yeah.
Are there similar behavior like pattern formation? The X states are there, which are also there any relationship for research behavior?
The point with it's all right. All these patterns depend entirely on classical effects, and the competition that is taking place is actually being governed by very macroscopic parameters. So the question of the quantum, it is incompressible, but it is a fluid whose physical properties are not, that is, it is not a fluid which would follow any fluid dynamics. And therefore, it is not, all right, there can be pattern formation over there, and if there is pattern, but the effects that would not be pertinent, one would have to look for effects which are quintessentially quantum and yet can be of in competition with each other. So I don't know whether one can look at it from.
I was thinking of domain formation in magnets.
Domain formation in magnets, that certainly is, again, I mean, more classical, I mean, than, yeah. So that is a competition effect, certainly. Yeah.
Okay, I think that is a lot of questions. So let's thank the speaker once again. And I now request the Co-Vice Chancellor.
So, on behalf of the university, we would like to present the.
Thank you very much.
This is a famous umbrella.
We are honored to have Professor Jayanta Kumar Bhattacharjee among us. We are thankful for his wonderful, motivating and inspiring talk presentation to the University of Hyderabad. For making such a distinguished lecture grand success, I must thank all the faculty members of the School of Physics for their initiatives and Professor Bindu Bamma, Dean, School of Physics, for sending her consent and recommendation to the Honorable Vice Chancellor. Then, of course, I thank Professor Apparao Podile, Vice Chancellor, and his office for sending invitation to Professor Jayanta Kumar Bhattacharjee and making necessary arrangements for his travel and accommodation. Thanks goes to Mr. Ashish Jacob Thomas, our PRO, and his office, especially Vijaya, for announcement of the distinguished lecture. Thanks goes to Professor Bindu Bamma, Dean, School of Physics, and her office, especially to Mr. Shekhar, Mrs. Deepika, and Keshava for arranging local hospitality. Thanks to Professor Arun Agarwal, Pro-Vice Chancellor, University of Hyderabad, for presenting over the session of the distinguished lecture. Finally, thanks to all of you for your kind attention.